Okay, so let me. So I can see that not all the people are in the class, but there are many students. So you have the privilege to take this decision. So you have given a quiz, almost two or three quizzes actually. If I include the mid-sem, and you have two more assignments regarding the that you need to submit in November. So the spectrum and the reaction kinetics, you have not given any quiz, and also no assignment. So what would you prefer? I mean, do you prefer to give one more quiz on this? I mean, maybe on the first week of November, or would you prefer the assignment? I mean, please feel free to interact. So what is your opinion? Let me know from you in the class only. So you can write in the chat, or you can switch on the unmute yourself and you can tell me. And probably Venkat will not take any class test. He will take the NSEM. Please be quick so let we can discuss more questions. So if you are not writing, let me start the class and you can write after discussing among yourselves, and let me decide. So if you want to give any quiz, I mean, at least either a quiz or an assignment, and all the quiz marks and all these things, even if you can see, these are not final for the mid-sem and quiz too. I today after finishing the class in the next week, you will get all the marks and for the quiz, all the quizzes and mid-sem and all these things, right? So we are discussing that regarding reaction kinetics, what could be the question? So what you have learned, if you remember, you have so you have done the ligand substitution reaction, right? Ligand substitution reaction. So there were different mechanisms. So the first type of question is that you will be given the rate, dependence of rate on dependence of rate on, let's say, it may be substitute this substrate or the incoming, anything, right? So depending on that, you have to decide about the mechanism of the reaction. Right. Number two is that you will be given two sets of reaction to compare the inertness or lability of the complex. Here a little bit of problem is there, because as you can understand, inertness or labile, even if more or less similar, it depends on the dissociative or associative. But look at the question first. So from the question, if you find that if the rate is given that this rate is faster than this one, so you know that which one is labile and which one is inert. So if you know the answer, then you give your you frame your answer in that way, that what are the factors that actually affect. So if you remember, I mean, you may not remember that what is the inert, and this CFSE gain is one of the important CFSE gain. So if it is dissociative, and just remind you, if it is dissociative, then if you have a octahedral complex, it will go to either square pyramidal or TBP. Both of them are more or less same, or TBP, and you will be according to the CFSE changes. And if it is associative, then this octahedral 2 7-membered in that 7-membered, mainly octahedral framework remains and it is called wedge octahedral sometimes. So here, what is the trick? The trick is that if you have, let's say, if you have D0, D1, D2, you see for both the cases, it is the electron is in the lower, I mean, in T2G orbital for octahedral complex angle, T2G orbital, and even if it is 5-membered or 7-membered, there is not much change in CFSE. I mean, you are not losing the stability. So mostly for both the cases, they are labile. Right, so you know that they are labile. Now, if you have high spin, so if you have high spin complexes, then if you have mostly D4, D5, D6, D7, and in most of the cases they are labile in both the cases, but mostly D3 and okay, and the low spin complexes are, so low spin complex is possible in case of this D4, D5, D6, D7, all these things. So low spin complexes are generally inert, because from octahedral, as there are 3 orbitals are in similar position, so whatever way you go, this degeneracy is a little bit compromised, and this once this degeneracy is compromised, the CFSE always there is a unstable, I mean more unstable. So in that case, it becomes generally they are inert, and D3 and D8. D3 is high spin, low spin similar. They are mostly inert complexes. Right. Another factor is the charge on the complex. This is very common sense. Charge on the complex, because once you have high charge, then they don't want to lose the ligand in any way. In dissociative, they don't want to lose the ligand, and thus this becomes the inert. Right, so these two and then the geometry. I mean, you know that in tetrahedral and the geometry is, you know that four uh, coordinated are much prone to substitution, and thus they are also used more in catalysis. Four coordinated are much prone to substitution. So is that clear or anything I need to discuss more? Is it clear? I mean, for the timing. So now if you start practicing, then you may face some problem and you can come back to. No response. Okay, now the second thing is that what is happening while I we are checking the this quiz questions. So there, as I told you, that there is one problem that some people are writing more things and trying to explain things in in great detail, but sometimes this is missing the actual point. So even if I understand that you understood the concept of that part or answer, but sometimes you are missing some a crucial part of this. So once again, I'm telling that for any competitive exams or anything GRE or I mean, even if it is not chemistry, whenever you are pursuing any subject, so it is very, very important that you read the question well and you try to understand first that what that question wants. I mean, do not write more than what is expected, and also in that process, don't miss the actual point that gives you that I mean proper answer. So so I kept very easy questions initially, so that I mean all of you know. But first, I shall ask you that what point should contain. I mean, answer should contain that particular point. So then I shall tell you. So you just read the question. Can you read the questions? Can you read the questions?
Yes, ma'am.
Okay. Now, this the question is very easy one. I mean, you know that it has been taught, or you know the most of you know the answer also right now. So tell me the points which what should be there in the answer. Please do not waste time. And it is very easy question. So please let me know. I'm not telling you that you have to, I mean, define right now what is data point, but what should be when what should be there in the answer that I want. You don't need to answer the question. You don't need to write it right. I mean, at this moment. So please suggest. Please suggest the answer. What should be there in the question? The suggested reason. Reduction of B. if you people do not, interact, then what is the point in, in discussing, right? Please suggest something. Yes, electron delocalization on metal orbital. That is fine, but your point is, so electron delocalization, fine. Please, if possible, then answer by electron delocalization. Yes. So here the point is the Raka parameter. So you can define B first. Define B, and then theoretical B is this, that is already written, you don't have to write. So, but you can write just one line that uh, complex formation changes the value, and then this answer, this delocalization, explain a little bit, and then you also use the term nepheloxetic effect. This term also you use. So this point must be there. So define B. So until and unless you define B, there is no meaning of electron delocalization. So first of all, you define that what is Raka parameter, right? And then you go to the any answer, any other answer, upon you somebody has given an answer. So that it will take 4 to 5 lines, and that will give you that, the term electron delocalization is in the explanation, what is B, and this nepheloxetic effect. Okay, the next question is that this last day I have discussed. So please, this table part you just ignore, because already the value is there. So the electronic absorption, it is given this, assign these 3 bands to electronic transition. So the what you must first find out. So how do you approach the question? If one of you, even then you even if you say something wrong, please say something. So electronic absorption spectrum of this one. So what you will do first?
First, we mark the ground state level in the diagram.
So ground state. So first thing is that you have to make it what is cobalt electronic configuration, right? So before ground state, what ground state? Electronic configuration first, right? And then ground state. Or you really don't need this ground state for, let's say, this is D7 system. And this, if you are given this one, this diameter may be given, or you have to, from the ORGAL, you have to find out D7, and you will be given the transition. And if you are in the last day, you are in the class, then or you just go and see that for D2 and D7 and D3, D8, there are formulas. So formulas will give you which one is new 1, which one is new 2, and which one is new 3. And from there, you find out that what is the, assign this band to electronic transition. So go to the D7 system, you don't need to find out the graph. The first thing is the electronic configuration. Second, from that you get it D7, then you either go to ORGAL, or if you are given this picture, you will know that this is the Tanabe Sugana. And from there, value of this listed. So find out from there, you find out del oct, that is the 10 dq value, and then you define that depending on the ligand, this day log value actually changes, right? It is, this part is, even if it is not given, because this 9300 maybe is given for a particular ligand, and this with water the del zero value is just like that. Right, this is very easy, but this part is very important, as you can understand, for all purposes, that for D2 and D3, there are, I mean, D2, D7 and D3, D8, you have this new one is equal to, for D3, this new one is equal to actually 10 DQ, and for D2, I right now want maybe 8 DQ, and the new 2 is equal to 18 DQ, like this, some relationship is there, and this relationship is very important for the answer. Relationship you have to remember. These things will be given, and from here also you can find out if this table is given. Actually, you can find out, and generally, in NET always it is not given. I mean, generally in class exams we give it. In some other exams also these things is given, but in NET sometimes they give very small question, like for D3 as D1 is equal to 10 DQ, they don't give this this figure. Okay, the next one is this one. So what you should know here, what you should know. This one is this clear for all of you? Let us go to the second hard question. Quick, please be quick. So to understand the Jahn-Teller distortion, what the first of all, what do you need? To understand Jahn-Teller distortion, what is the first thing you look for? Please, all of you, I mean, some of you answer. What is this? I mean, after all the classes, if you can't tell Jahn-Teller distortion, what you are looking for? For Jahn-Teller distortion, what do you look for answering the questions on Jahn-Teller distortion? Anybody? D electrons. Okay, D electrons means, so this is the point. Don't write D electron. It is the, this term is very important. Electron configuration. Electron configuration and distribution of D electron. Or you can write D electron configuration. Right? Because D electron configuration, so out of this D electron configuration, what you should look at it? First of all, what is the geometry? So octahedral or T or square planar or something, and then you come out of that uh, I mean, if it is D2, then that nothing matters actually. And then you should go for whether high spin or low spin. And then you have a series of, you must remember, either you have to remember or you have to draw it. Like if it is octahedral, and if you draw like this, then you know that this configuration have this Jahn-Teller distortion. Like I mean, you have to you have to find it out. So if it is D1, then also Jahn-Teller distortion. If you have D2, then also Jahn-Teller distortion. Like this, you have to, or you, if it is, whether it is, if it is high spin versus low spin for, let's say, D7 and all these things. So low spin D4, then you have to find out in that way that whether that particular d electron configuration gives you, whether this particular d electron configuration is susceptible to Jahn-Teller distortion or not, and then you find out. So for this Jahn-Teller, I'm telling you, Jahn-Teller is extremely always, always there are questions, always there are questions from Jahn-Teller. And the questions, if you just remember the things, or if you understand, you can deduce it there, and you can answer that question. So don't miss that question. So that uh, initially you just read the d electron config that are prone to Jahn-Teller distortion. Right. The next one is that this question. Can you read this question? Otherwise, I need to. Uh, I mean, expand it a little more. Please let me know. Can you read the question?
Yes, ma'am.
Then please read it, and then it will take 1 minute for you. So I think you have finished reading, right? Now let me know that whether the question, you have understood the question or not. So if you do not really interact, then maybe in the end sem we need to take a face-to-face oral. So please interact. Otherwise, how do I know that all of you have read, or whether you have read it or not? Read
Ma'am, the
the.
first part of question is not clear well. Means the conformational change.
Okay.
I do not
That's the
got that.
point, that you whether you people are do understand, because this is a very simple question. So the first thing is that what conformational change does the BPY ligand undergo? So now you know that BPY is a chelating ligand, right? That you know.
Yes, ma'am.
Okay. So you know that, then you just see that if a metal is approached, then if these two nitrogen is in the different side, then is it possible that it bind to this metal? So before it uh, uh, joins the metal, it should be like that. See, the answer is very easy, but that's the point, whether you do understand or not. What is the, is it clear? So these conformational changes required. So the rotation around this single bond is required so that bipredyl can act as a chelating ligand. Is it clear?
Yes, ma'am.
Okay. Now the next question B. There is an ideal dye point. Is there? An ideal dye should absorb light over the whole visible range, and the extinction coefficient should be high over the whole absorption range. So, what is the point? Dye sensitized solar cells. So, now you go back to the first point. So, these dye sensitized solar cell. Now, if you have a, so I mean, very briefly, I am telling you what is the purpose of this thing. That you we always are discussing about the alternative energy and all these things, that we must use the solar energy and all these things. Now, as you understand in layman's uh, term, what you can tell that even if you generate energy, what is the problem with the generate energy? That how would you store that energy? Number one, and how would you propagate that energy? Right? I mean, how would you? I mean, dissipate or you propagate the energy? How would you transfer the energy? These are the basic things. So when you are thinking about the molecular level of this energy gaining, so the first thing is that if you are want to take the solar energy, so there is a lots of energy in the visible region. So the, if some compound that absorbs only the ultraviolet ray, then it is then it will take a little amount of energy from the all the solar things. So you must have such structure that absorbs all the visible, that can absorb visible light as well as the all the light, so that it will actually it can ultimately it can absorb a lot more energy, and it can absorb all the light over the all visible region. And the extinction coefficient, because the intensity of the light must be high, I mean what is absorbing, so a lot more of energy it should absorb. So this is the point. And then if you are given this term extinction and not the intensity, extinction coefficient, because in that case, if you remember this extinction coefficient term, I told you, you may not remember, again I am telling you that if it is DD transition, then what we have said, that DD transition is forbidden for forbidden in terms of Laporte selection rule, right? And we are banging only on spin selection rule, allowed to spin selection rule. And thus, if you want, you go and read back, then the epsilon is very low. But in that case, what type of, so here you have the ligand, you have the metal. So what type of absorption? What type of absorption? You have high epsilon, that is the MLCT. That is the MLCT, or you can say charge transfer. It may be ligand to ligand charge transfer. So this is the answer. This is only the thing, that you read the question and what type of transition. So this is actually MLC. You read it, now you correlate it, you can understand. But the question here, you are given this question whether you could understand the question or you could find out that what is the point that has been discussed. So now you read it and then come back. Please let me know what is the origin of the acceptor orbital and what is the general name for this. So origin of the acceptor orbital, what we have seen, that if you have vacant pi star, right? Vacant pi star on the ligand and all these things. So these bipedal type of things, they have pi orbitals, and then you have this answer. So now you read the question. And let me know, do you feel now you understand the question or please let me know. Otherwise, I need to explain to you a little bit because these questions are easy, but there will be, big question. So you have to read the question, you have to understand the question, but the answer is basically very easy answer. If any part of the question you do not understand, please let me know. Can I move to the next question?
Yes, ma'am.
Okay. Okay, now there is the values of epsilon max for most intense absorption in the electronic spectra of these two differ by a factor of 100. So now, again, the same way, but there are another point you need to check here. So what is that point? What is that point? Cobalt in both the cases in the cobalt 2 plus. Please, what are the answer? This is cobalt Cl4 2 minus, and this is cobalt H2O whole 6 2 plus. So what are the difference? Electronic configuration same or different? Same, right?
Yes, ma'am.
Then what is the difference? What is the difference? This is extremely easy. I mean, what is the difference between these two complex if the electronic configuration is the same?
One is tetrahedral, one is octahedral.
Yes, tetrahedral and octahedral. So that's not the answer. So why? What happens? So now, what is the selection? So if differ by a factor of about 100, then what is the difference? More symmetry, right? Symmetric structure. And only Laporte forbidden. Here also Laporte forbidden, but less symmetry, right? Only that part. I mean, that if you write tetrahedral and octahedral, and the symmetry, the octahedral is much more symmetrical than tetrahedral, and that's give you the answer. Next. Next, this I have discussed, but one point I do not remember whether I mentioned it or not. So, if you remember, please let me know. Assign the two absorption. Last day we did it exactly with this particular thing. And here, I mean, as you can see that there is 700, 1700, 200, and in some cases you will get it is 1700, 800. So this is more or less same because it sometimes it depends on the solvent and all these things. So it's the same question. So what is this that electronic absorption spectra? Even if you do not remember, let me know how do you approach. So for any absorption spectra, what do you do? First of all, what do you do? For any electronics absorption spectrum problem, how do you approach? I know that some of you are there in the last class, so please let me know. So if you know that this is BH2O whole 6 3 plus, so what is the first thing you look for? Today I also I told you what do you look for?
Electronic configuration.
Yes, electronic configuration. And this is probably D2, right? And once you have D2, what do you look for? The transition. Okay, so here what are the transition? If for this question you can see T2G2, T2G1, EG1, and it is EG2. Now, if you just look at these transitions, so this is one transition and this is one transition. And if you look for this transition, you see this is uh, forbidden also spin through spin selection. Spin selection rule also it is forbidden. So what is that you just go to the spin selection rule, find out that what is the criteria, and then if you are satisfied, you just go after the class, and this is the answer actually. Okay, now can you read this question? Again, the same approach. So what happens? TiH2 whole 6 2 plus and TiH2 whole 6 3 plus. What are the, so it, can anyone I mean, from any source, can you tell me what are the electronic configuration for both the cases? What is the electronic configuration of titanium in both the cases? I mean, they are different. Okay. What happened? What is the electronic configuration?
D2 and D1.
D2 and D1. So now what is the difference? Right? So now you go to the question, two well separated bands, right? Two well separated bands. So I'm not giving you this is the question. So now you look for the transition. So one is D2 system, one is D1 system. D1 system, basically it should be one peak, but for Jahn-Teller, you see a very close folder. Right? And the other one is just for D2. One we couldn't see because of very low intensity, and other two we can see. Okay, here also again the electronic configuration, right? Both of them and chlorine, you have to find out whether chlorine is a position of chlorine in spectrochemical series. The electron configuration, then position of chlorine. So mark it whether high spin or low spin, and then it is mostly Jahn-Teller, and then go to the electronic actual geometry, and you'll find that why it is flattening tetrahedral. Okay, now you have some questions from these the reaction kinetics. So can you read the questions, or let me increase it a little bit. I have not kept much questions. I can give Can you read the questions right now? We have not finished the discussion about the what are the topics that reaction kinetics can have the questions. Okay. So I shall do it. First, let me first these four questions. Let us understand, and then we'll go. So that we have discussed. We have discussed. So what could be the how do you approach?
Ligand field strength.
Yes. So you will just see that gain or loss in CFAC, right? And you will find that which one is so first the electron configuration with respect to, because here it is cyanide, here it is water. So you will have the high spin or low spin. So my point is that I'm requesting you repetitively that if you do not try some of the answers, these answers, I mean, for this, whatever you have read through this, I mean, for the last 23 days or maybe 20 days, all these things you do not have to remember if you just practice a little more this uh, problems. If you practice some problems, you really do not have to memorize things. It will be there because you don't have to remember that what is the chromium 2 plus or chromium 3 plus, because once you go through the practice problems, you will see that there are very limited things that actually people give. I mean, this chromium, cobalt, and then this titanium and vanadium and copper. These are the most mostly these are the given electronic configurations. So D2 and D3 and D7, D8, and also that what are the ligands that in spectrochemical series. So what actually you need to remember the electronic configuration of metal, and this is very important. Number two, for all kinetics and electronic spectra, stability of this something, day logged value. So this is important for all. So for bonding, day zero value, electronic spectra, reaction kinetics. For all, this is very important. Number two is the nature of ligand. So nature of ligand determines you the geometry. Number two gives you the high spin, low spin, and also this spectrochemical series tells you that high spin, low spin means spectrochemical. The charge on the metal. Number four, size of the metal ion. Number five is the steric factor. Right. So these things are important. So now go to the, this is fine. What is the next question? Why is the existence of a series of entering groups? Why is the existence of a series of entering groups with different rate constant evidence for an associative mechanism, A or IA? This is very easy question. So this question is not like uh, approaching a problem. This is a straightaway question, and in that case, you have to explain a little bit about the associative mechanism or this IA mechanism. So this association part is very important. So as the entering group is different, so the association with a particular, let's say you just take one particular example, or you can say like ML6. If it is ML6, you can say this is the octahedral complex, and if it is associated, then you need to add this one, and these approaching of y depends on what are the things, that is the geometry of that atom, that existing metal complex and all these things. And for a, let's say, very less bulky ligand can associate very easily, and a statically hindered or bulky ligand can associate very slowly. So in that way you have to explain this one, right? The next question is that you read the question and again please, I mean, why it is magnetic moment is given. It's very easy to understand. And once you do the problems, you will find that if you remember certain things, then the electronic spectral questions are also very easy. I shall come back. I shall again, as we have a little time, so we shall part by part we'll go. What are the things that you have to remember or do? So the 12.3, please read the question. So you have not read the magnetism. You will read it a little bit after Venkat will give you. So the magnetic moment, from the magnetic moment, as you understand, you can find out the number of unpaired electrons. And so once you have the number of electrons, so first you have what you have to see, what is the chromate 5. So from there you have to find out the electronic configuration, and after this electronic configuration you have to find out the number of unpaired electron, and number of unpaired electron will give you the high spin, low spin, and or this concept, and from there you go back and then you find out whether this is a labile or inert. Dal 12.4 question is a high school question, very easy question. It's complex formation, so I kept it, but I really don't want to know the answers from this. So let me give you a time of 5 minutes. So you please think what you really, if you need any explanation for this. Otherwise, I'll just summarize that what we have gone through and what would be the questions. I mean, what are the important things that we discussed, and for all the three topics, and what are the questions on the topics, what are, on what topics you can expect the questions. Okay, so just think for 5 minutes. So if you are ready with the questions, I mean, you can tell me. If you have any question regarding all these chapters, the spectra, the reaction kinetics, the bonding. Otherwise, let me start with this. So the first thing that we have started with is the bonding. So the bonding has started with the understanding of metal orbitals, nature of ligands, bonding interactions between metal and ligands, and then the degeneration of the degeneration the state of the orbital when ligand approaches the metal, right? And then you have the different structures, not structures but geometry. So here the main point is that depending on the metal and ligands, you have geometry, and that geometry gives you different energy d orbitals, and this del not octadel, del value differs considerably. So to answer the questions from bonding side, what you really need, first of all, you must know very well about the metal d-electron configuration. Number 2 is the nature of ligand. Number 3, after the interaction, what geometry it will adapt, and after that geometry, what will be the d orbital or energy status d orbital. Right? Is it okay, or do you think that there should be many more points? Please suggest something. If you feel that something more is there, then please let me know. You have read a lot about this. Okay, another thing I missed, I'm coming. I mean, it's really difficult for me to remember all the things together. That is as this the most important part of transition metal, the oxidation variable oxidation state. So these diagrams, Frost, Urbai diagrams are also important. Right? So please let me know whether you think anything more is important in bonding. I mean, these four topics include actually a lot more things, but whether you need to add any more topic or not. So those who are in the class, please respond. Do you think anything more is there? Or these four includes all the aspects of the bonding? No suggestion. You decided to be non-interactive here. Okay, next is the electronic spectrum. So the first thing is this will come as a separate problem as ground state determination. Then the spectroscopic term, I shall not give much here because spectroscopic term symbols from symmetry elements that has not been taught. I mean, only the required spectroscopic term I told you. For that reason, I shall not give you much on this. Only this, whatever T1G, A2G, T2G, this is for D2, D3 system, and for D1, D3. That term will come, but not. It's not that for all this ground state or the excited state, what should be the spectroscopic term, that I shall not give here, but you will learn it in Omlan class and then you can correlate. And then comes the real spectra. And from real spectra, you have the relationship between the mu and B, mu and 10 dq values. These are very, very important. And then you have B, the nepheloxatic effect, and correlation of with B dash, find out beta. Then you have the MLCT, charge transfer spectrum. Right? The third is the reaction kinetics. Number one is the substitution reaction. So here comes the mechanism, how to find out, I mean, from the rate law, volume change during volume entropy. Volume change I shall include during reaction gives an idea about the mechanism. Number four is the complex. And very important is the base hydrolysis. And here some terms are very important. Ligand field activation energy and base hydrolysis. This is very important. It will be given 2 or 3 types of reaction, and you will find that for one type of one of them, this base hydrolysis is the mechanism, and that actually changes the definition of, I mean, this. I mean, the reaction will be reaction will undergo from a completely different aspects, and you cannot compare these two because one of them went through the base hydrolysis mechanism and another through some other mechanism. Okay, and then these are the things, and then you have the redox reaction. And one of the reaction, if I remember some things, I'm coming to this. And then redox reaction, you have inner sphere and outer sphere. Okay, so I mean, inner sphere, outer sphere mechanism and all these things. So one question I remember, I may not be completely right. I mean, let's say you have taken some compound with M, let's say 1 and 4, and let's say, let me keep Cl2 like this, and this is 2 plus, and you want to, this is 3 plus, and you are this is the catalysis, or this is the helps in the reaction of, let's say, Fe2 plus to Fe3 plus. So what happens? This reaction goes to this part, and this one will go to 2 plus state, right? Now the question may come that this is the reaction. To catalyze that reaction, we have used this this compound. Now you can find this complex and intermediate. SCN4 minus 2 plus, water is better. So this complex is an intermediate. So if this is an outer sphere reaction, then these ligand sphere will no way interact with the iron, but it is an inner sphere reaction, so that this MSCN iron at some point of time these type of things are happening, and this reaction is, I mean, momentarily you have this complex, you get this complex as the intermediate. So these type of questions here actually comes in inner sphere. I shall give you some questions, and then you have from redox and this Markov equation. Very simple. Very simple relationship. Only okay. So here, I let me end, and then I am waiting for your questions. So please, I mean, this is the last class, and please let me know whether at any point you have any queries or not. Or again, I'm telling that whenever you feel, you can ask me questions in any of the format. You can ask the question to the TAs also, and if you feel that they sometimes even very busy, or myself too, but we will get back to you at some point. I mean, it may be a little late, but we will get back to you. So if you do not have any more questions, so all the best, and please study well. And these transition metal complexes really will help you in all these exams and all understanding of this chemistry throughout. And I can resign from the class if you really do not have any question.